talk is joint, the topic of the talk or the result of the talk is joint with Ilya Rips and Catherine Tent. And my talk will be divided into the following parts. I will do an introduction. I'll talk about sharply two transitive groups. Which I will abbreviate by S to T groups. I will talk about involutions in sharply two transitive groups. I will talk about non-trivial abelian normal subgroups of sharply two transitive groups. Then I'll talk about the main results. 6, the construction. And 7, sharply two transitive groups of characteristic 3. All of these 7 parts in 1 hour, less than 1 hour. Okay, so I guess I'll have to. I want to play a little bit with the board, so I'm not sure I'll be able. There are 2 boards here. So anyway, I'll start with the introduction. So let X be a set, and let sim X be the symmetric group on X, a subgroup G of sim X is said to be sharply K transitive, sharply in parentheses, if for any pair of K tuples x1 up to xk, y1 up to yk of distinct elements of X, there exists in parentheses a unique sigma in G such that xi sigma is yi for all I in 1 to k. So I guess you know this definition of sharply K transitive group. Now if G's sharply is sharply 1 transitive, then we say that G is regular in X. Okay, so this is the notion of regular. The finite four transitive groups are the symmetric group n for n larger or equal than 4, the alternating group n larger or equal than 6, and the 4 Mathieu groups M24, M23, M12, and M11. Now the full proof of this fact requires the classification of finite simple groups. The foolproof requires classification of finite simple groups, but several cases were known much earlier than the time that the classification was known. I'm continuing with the introduction here.
So here it's Sharpie or not?
No,
No Sharpie.
just any four transitive. Any finite four transitive group is listed here. Okay, so of course, I just note that Sn is sharply n and n minus 1 transitive, and an, or alt n, whatever, n is sharply n minus 2 transitive, and a theorem of Jordan that dates 1872 says the following: theorem Jordan, 1872. Let G be distinct from symmetric n, alternating n, be finite K transitive, sharply K transitive of degree, I might omit some letters here and there. Anyway, of degree n. Then, if K is larger or equal than 4, then either K is 4 and n is 11 and G is M11.
11. You wrote n equals 1.
What?
You wrote n equals 1.
Thank you. And G is M11, or K is 5, N is 12, and G is M12. Okay, so this is one theorem that was known much earlier. Another theorem which is important, or which is related to what I'm doing, is a theorem by Marshall Hall, 1954. Let G be four transitive, not necessarily sharply, and not necessarily finite on X. Assume that the stabilizer in G of 4 points, of four distinct points, is finite of odd order. 4 distinct points, x1 up to x4, then G is S4, S4, S5, A5, A6, A7, or M11.
Here is for every side.
I'm sorry?
S5. The second S4 is S5.
That's correct. Thank you. Okay, so in particular, there are no infinite K-transitive, sharply K-transitive groups for K larger or equal than 4. The Matthew group M11 of degree 11. Oh, the order is if degree 11 M11. The Matthew group of degree 11. It acts on a set of 11 points. Okay, so the interesting infinite sharply transitive groups are the 2 transitive and the 3 transitive sharply the 2 and the 3 sharply transitive groups. Of course, the one sharply transitive is not interesting. So that covers the introduction. Okay, so now I want to move to sharply 2 transitive groups. So let G be sharply 2 transitive on X, and let V be a non-trivial, should abbreviate this as well, normal abelian subgroup of G. Then V is regular on X, and of course G is a semi-direct product. I never write this sign, but anyway, I type it sometimes. VH, where H is a point stabilizer. In this case, we say that G splits. So this is the notion of splitting that is in the title of my talk. The sharply 2 transitive group splits if it's a semi-direct product of an abelian group and then a point stabilizer. Okay. Right. So in this case, we say that G splits. Now, as I wrote in the abstract to my talk, in 1936, Zassenhaus classified all sharply finite sharply 2 transitive groups in 2 papers. In the first paper, I'm going to move this all the way to over here. Okay, so in his first paper, he showed that a sharply 2 transitive group splits finite or infinite if and only if it can be identified with the group of all affine transformations X goes to AX plus B, where A is in F star, B is in F, and where F is what is called a near field. Now it is easy to show that to show that a finite sharply two transitive group splits.
What is a near field?
A near field is something which has the distributive law. Who asked? It has a distributive law only on one side, and I believe that the addition is not commutative.
Not assumed true.
I'm sorry?
The addition is not assumed true.
Okay, not assumed. Thank you.
And F is the set on which the group is acting.
Proper near field. What?
F is the set on which the group is acting.
F is the set on which a group is acting, exactly. And then, as I wrote, it is easy to show that a finite S2T group splits. So it has this form, and then in the second paper, Zessenhaus classified all finite near fields. So he classified all sharply two transitive groups. The answer to the question, well, maybe I shouldn't write it. The answer to the question of whether or not an infinite sharply two transitive group splits, that answer defied the attempt of many mathematicians ever since Zessenhaus results. What was known, or some of the things that were known, are positive results, namely splitting results. So some splitting results for infinite groups. As I said, finite groups always split. And so some splitting results are, in 1952, Jacques Tietz proved that if G is locally compact, connected, then G splits. A mathematician by the name, I believe, I don't know how to express this, Walling, I think it was 1986, he proved that if G is locally finite, then it splits. Then there was a result of Glasner and Gulko. Glasner and Gulko, where is Denise? Here. Glasner and Gulko just recently, Glasner and Gulko, proved that 214 or 213, 213, Glasner, Gulko proved that if G is linear, of characteristic not to G splits. Well, there was some additional restriction which I'm not going to be a little bit more precise. And then now in 214, the result by Glauberman, Mann, and myself, if G is locally linear, the techniques here and here are completely different, and it says that if G is locally different, locally linear, of characteristic not to G splits. Again, one should say also characteristic not zero. Anyway, more or less that's the result. And I'm not saying that these are all known splitting results, but okay, this is some set of splitting results that were known. And this covers the second part of my talk here, part 2. Now I'm in part 3, Part 3 is our involutions. Where's the eraser? Oh, it's somewhere here. Okay, so now I want to go to the third part of my talk. Oops, erased. 3 involutions in sharply two transitive groups. Okay, so if G is sharply two transitive on X, then G contains many involutions, namely elements of order 2. Indeed, if I take two distinct elements are distinct, there exists a unique involution in G flipping, that's the way I write it, X and Y, right? There will be an element flipping X and Y, and its square will fix X and Y, so it will be an identity. So those are involutions. So let I be the set of involutions in G, and this notation will prevail throughout the talk. I'll denote by the set of involutions by I. So let I be the set of involution. I is a conjugacy class in G, as is easy to see. Yeah, you can take any pair of elements or any pair of elements, and a pair of elements determines an involution. So I is a conjugacy class. Pick an involution. Then you have, let's see, what do I want to erase? Erase here. To pick an involution, there are two possibilities. Possibility 1 is that T fixes no point in X. The involution fixes no point. We write characteristic of G is 2, and we say it. Characteristic of G is 2. Char G is 2. 2, T fixes a unique point in X. In this case, one can show, and it's not hard to show, that the set of products of all pairs of involutions without identity is a conjugacy class in G, and it is true in any group that the set I squared is closed under taking powers. So, either A, the product of two involutions R times S is of infinite order. I hope you can see it from over there. Is of infinite order for all two involutions, distinct. For all two distinct involutions, the product of the involutions is of infinite order, or the order is a prime, and the prime is an odd prime. In this case, we say that the characteristic of G is 0, and we write char G is 0. And the last case, B, is that the order is P larger than 2 is a prime, is an odd prime. Well, I wrote larger than 2. Is a prime. And here we say that the characteristic of G is this prime, and we write char G is P. Okay, so this is the situation with involutions in a sharply two transitive group. Either they fix no point, characteristic 2, or they fix a point, then the product of any two is the set of products of any two, which is not one, is a conjugacy class, and the order must be either infinite or a prime. And I'm done with part 3. And part 4 is a short part. I want to say something about non-trivial, normal, non-trivial, normal, abelian subgroups of sharply two transitive groups. So let G again be sharply two transitive on X. Let V be a non-trivial abelian normal subgroup of G. Then there are then one can pinpoint those normal subgroups. If the characteristic of G is 2, involutions do not fix points, then V is just the set of involutions together with the identity. The set of involutions together with the identity is the unique non-trivial abelian normal subgroup of a sharply two transitive group of characteristic 2.
This is the split case, right?
I'm sorry?
This is the split case?
This is when you have a non-trivial normal abelian normal subgroup. This is what I call the split case. Whenever you're in a split case, you know to identify the abelian normal subgroup. It is this group, this set. It is this set if the characteristic is 2, and this is, of course, this is a vector space over GF2. If the characteristic is 0, then V is the set of products of the set of products of two involutions. It is a set, and it is a vector space over Q. And the last possibility is the characteristic of G is P, and then V is again the set of products of any pairs of involutions, and it is again a vector space over GFP. Okay, this is this part. So this is how non-trivial normal subgroups look like if they're there. Right. Okay, now I'm in part 5, which are the main results that I want to present. I hope I'm doing well with time. As I said, it was unknown whether any infinite sharply two transitive group splits or does not split since 1936 or even before. And so it does not. Theorem, let G be a group having, oops, I should have said something before that. Sorry. I should remind you, I should note that if G is S2T on X and one picks an element in X, then Gx intersection Gx to the G equals 1 for all G outside of Gx. Gx is a stabilizer of G in G of X. Because Gx intersection Gx to the G fixes X and Xg. Okay, so it is 1. That is, in another language, that is, Gx is malnormal. A notion not used that much by finite group theorists is malnormal in G. Okay, so one wants to look at malnormal subgroups of groups, and now I can state the main result, which is the following theorem: let G be any group, but we want it to have a malnormal subgroup A such that A has no involutions. Okay, for example, take A equals 1. Then there exists a bigger group G script. Then there exists a group.
So for you, a group is a permutation.
No, for me a group is a group.
So involution is just ordered 2 elements.
I'm sorry?
Involution is ordered 2 elements?
Yeah. Then there exists a group G having a malnormal subgroup script A such that 1 A intersection G is just the malnormal subgroup we started with. So the set of right cosets of A and G embeds in this set of right cosets.
This script.
Containing G.
Oh.
Sorry,
No, you have it because
I didn't write it.
it doesn't matter. A intersecting G is X.
I should have written it though. Containing G without script. Thank you. So that this intersection is A, 2, G is sharply 2 transitive on the set of right cosets of A in G. 3, the group script A has no involutions. So the characteristic of our script G is 2. And 4, G does not split. So here you have examples of infinite groups that do not split. Oops, that I don't want to erase. I guess I want to erase this. So this is the main result. And as a corollary, one gets that any group is contained in a sharply 2 transitive group that does not split. That does not split, and of characteristic 2. And the proof is, take A equals 1 in the theorem. Okay, so there are many non-split non-split sharply 2 transitive, infinite sharply 2 transitive groups, but all of characteristic 2, and I've done part 5, so I'm left with part 6 and 7. I still have some time, right? Right, so yeah, so part 6, the construction. The construction. I don't like this. Okay, the construction. So what do we do? So one thing to keep in mind And this will explain, this thing that you're going to keep in mind, if you want, will explain the case division that will happen, that will follow, that is to follow soon. So one thing to keep in mind is this. If you have a Mall-normal subgroup of any group, if M is in K is Mall-normal in K, then any coset of A in K will contain at most one involution. Any non-trivial. Coset of M in K will contain at most one involution. Indeed, if MT equals MS distinct from M, if MT equals MS distinct from M, TS are involutions. Then the product TS is in M, so the product TS will be in M and in M to the T, because T inverts TS, so the product will be in the intersection, and since T is outside of M, this must imply that TS is 1. So any non-trivial coset of a Mall-normal subgroup has at most one involution. And I will use this. This will explain the case division, which is to follow. Now I'm going to draw this board all the way to here, which gives me this board. I'm moving to this board. Okay, so now I'm going to show you how to construct a non-split sharply two transitive group. Not with all the details. Okay, so let G be a group having a Mall-normal subgroup A such that 1 we want A contains no involutions. 2, there is an involution T outside of A. And 3, G is not sharply two transitive on the cosets of A. Okay, start with such a group. We want to add elements successively, maybe is the right word, add elements to G to enlarge it to eventually get this bigger group G. We do this very slowly. This addition of elements, we do it very slowly. Adding in at each step one element. Adding step by step. Adding one element in each step. We add element of infinite order. We add f of infinite order to G.
Sorry, how is G acting on G minus A?
On the cosets. Those are the right cosets of A and G. I don't know, some people write it like that, but then you can think it's the left cosets. I don't know. I write it like that. I'm not sure that's the... I don't like it too. Anyway, I didn't find a better notation. So anyway, okay, so we add one element f of infinite order to G. So G is just the group G1 to get another group, a bigger group. G1, the group generated by G and F, and we let A1 be the group generated by A, F, and TF V inverse, where V, where I didn't tell you what V is, what is V? So V is an element that you cannot reach by an element of A from the coset AT, so such that V in G satisfies AT G is not equal to AV for all G in G. Okay, but we want to add we want to add the element F in a controlled way. We want
So it seems that you assume that you're not acting transitively.
Yes, exactly.
I'm not acting transitively. G is not sharply too transitive. Since A is malnormal in G, the action is if the action would be transitive, the action would be sharply too transitive. Yes.
In the sense, the witnesses that it is not transitive.
This is a witness that it is not that it is not transitive. If it would be transitive, this will fail. Okay. Right. So V is a witness to the fact that it's not sharply too transitive, but we want to add the element. We want to add F in such a way that our group G1 behaves nicely and in a controlled way. And so how do we want to add F? We want to add F so that the group G1, so that the group A1 intersects G will be the group A, so that T remains outside of A1. 2, we want A1 to have no involutions. And 3, we want, of course, the main thing, A1 non-normal in G1. Okay, so now I'm getting to the case division that I mentioned earlier. The case division when I talked about cosets of a malnormal subgroup. So there are two cases. Case 1. Oops, I should say something before that. I'm sorry. I should notice, or I should note, that we can replace V by any element in the double coset AVA, because if A1 TF is AV, which I should have noted, the choice here automatically says that A1 TF is AV. This is by the A1V, sorry. This is just by the choice of F. So F is the element that will take this coset to A1V, and we can replace we can replace V by any element of this double coset, because if we can get from A1T by F to A1V, then A1 TFA equals A1 BVA for all AB in A. So if we can get to V, we can get to any element in the double coset AVA. Right. Right. So so now I can talk about the two cases. Yes.
I'm wondering if you'd better to erase this board, because
I'm sorry.
could you erase the right board instead?
Sure. Yeah, that one was before that one. Thank you. I don't know. Maybe I can even move this one too. Wow. There are many options here. Too many. Okay. So anyway, I am saying that I can replace V by any element in the double coset AVA, and now there are
Maybe
two.
you are asked to push it a little further.
I can push it a little further. This is okay?
More.
Even more? Even more, all the way.
I think Peter is now happy.
Good. Okay, so two cases. Case one, this double coset has no involutions. If this double coset has no involutions, there are basically no restrictions. We just take G1 to be the free product of G with a group generated by F, and that's it. This is G1. It turns out, and not hard to show, that the element T, F, V inverse has infinite order in G1. In G1, so, and that the group A1 is just a free product of A with a group generated by F and the group generated by TF V inverse. Free product. And so A1 intersection G is A, is automatic, and then A1 has no involutions. Is automatic, almost. Involutions, and what else did we want from A1? We want it to be malnormal. Here you have to work. One has to work, some work. I said this is joint with the ribs, so it's doable. Okay, so I'm erasing here, and so some work is required to show that A1 is malnormal. In G1, and we're done. Case 2. Since we can replace V by any element in the double coset, we can assume that V is an involution. That V is an involution. Okay. And now what do we want? As I wrote earlier, we want A1 T F to be equal to A1 V. And we want A1 malnormal. But this says A1 and F is going to be inside A1. So this says A1 F inverse T F equals A1 V. Okay, and V is certainly not inside A. A does not have A1. A1 will not have involutions. So I have a coset. I have two involutions. This is an involution, and this is an involution. I have two involutions in the coset of A1. So we must require that the conjugate of T by F is V. And so one draws the magical tool. Well, I don't know. That's probably not the right word, but one draws the the magic of Ilya-Rips, okay, and one looks at, I shouldn't call you a tool. So anyway, one defines G1 this time to be an H&N extension, HF, T to the F is V. And so notice that in this case, F inverse, in this case, T, F, V inverse is F. TF V inverse is F. And since A is generated by, A1 is generated by F, and this guy is just, A1 is generated just by A and F. And so then A1 is just generated by A and F, and it turns out that it is a free product of A and F. And again, A1 intersection G is A. A1 has no involutions. And what did I say earlier about malnormality? I mentioned Ilya-Rips, so so A1 is malnormal. You have to work on it. In G1. So that's it. You move from one situation with A to the next situation with A1, and you solved one element. You managed to move one more element. You managed to move AT to one more coset of A, to the coset AV with this element F, and passing, and I write it imprecisely, passing to the limit. One gets the groups G and the subgroup A that I mentioned in the main result, and the last thing to show is that G does not split, and since G is of characteristic 2,
So why possibly worse? You moved one more element. You increased the G mod H.
Yes, but you increase the G mod H. Yes, but you go on.
Put all elements on a line. Yes.
Okay.
Ultimately, every element will be treated.
You increase, but you perceive what you increased.
You just have to observe that on limit stages all the conditions are preserved.
Okay, so now I just have to say why I said that this statement is not, it has to be made more precise. But anyway, G, I want to say why does this group G doesn't split? Well, this group G is of characteristic 2, so if it splits according to what I said about involutions and about non-trivial abelian normal subgroups of a split group of characteristic 2, the set of involutions is an abelian group together with 1. So in particular, any two involutions in a split characteristic 2 sharply two transitive group, any two involutions commute. So the only thing you have to do is to find two involutions that do not commute. So in case 1, one shows that we have F inverse TF, F inverse TFT is distinct from T F inverse TF because these are canonical forms of elements in a free product. So they're distinct. So the involutions T to the F and the involution T do not split just in the first step. Just in the first step, you already produced involutions that do not commute. And it's the same case in the H&N extension. In case 2, when you have an H&N extension, what you have is you pick an involution distinct S in G1, which is distinct from T, and there is an involution distinct from T because T is not in the center of G1 because A1 is malnormal in G1 and T is outside of A1. So T is not in the center of G1. There is an involution S in G1 which is distinct from S, and again, for the same reason, you get that S and S to the F do not commute. And you're done. So this is the idea of how you construct. And I have some time, right? I still have some time. I wanna quickly speak about sharply two transitive groups of characteristic 3, S2T groups of characteristic 3. And I want to show you quickly why do those split, always. Sharply two transitive groups of characteristic 3 always split, and here is a lemma.
This is old, no?
I'm sorry?
This is old result?
This is an old result, and I'll prove it. I'll more or less prove it. Let G be S to T of characteristic not 2. Any S to T of characteristic not 2, I have lots of blackboard space, so I'm going to move to this area. Okay, can erase this. The plan of the talk. Okay, then, and let J be an involution in G. I is always a set of involutions. Then the following are equivalent. 1, G splits. 2, the elements of Ji equals Ij commute with each other. And 3, J to the A, Bj, AB equals J for all involutions AB. Proof, 1 if and only if 2 is well known. I'm not going to prove it. Yeah, so let me show that 2 implies 3. By 2, and since all involutions are conjugate, I know that the set of elements here commute with each other for any involutions. The set of all elements here commute with each other because all involutions are conjugate. And so, if I take the element JAB, JAB, and I put parentheses here, that's equal to JA, AB, B equals to J. So J to the JAB to the AB, JAB is indeed equal to J. Now to the other direction, I want to show that 3 implies 2. Again, since all involutions are conjugate, I can assume that C to the ABC, AB equals C for all involutions ABC. Okay, so I get that J to the ABJ, ABJ is J. That's the assumption in 3. And I also get that A to the ABJ, ABJ equals to A. Because this goes away and this is the same, has the same form, BJ, ABJ. Okay, so this element centralizes 2 involutions. So it fixes the unique fixed point of both involutions, so it's 1. So ABJ, ABJ is 1, and then you get AB, JA equals JA, AB. And so you get 2, and now I need another 2 minutes to prove from this as a corollary. If G is S2T of characteristic 3, then G splits. I'm going to show this property for a group of characteristic 3. Well, if you have characteristic 3, namely the product of any two involutions is of order 3. So this implies that u to the vu equals v for all involutions. The characteristic 3 property implies this. You can check that this means vu to the 3 is 1. And then you have j to the ab equals j to the a to the j, jb, a to the j, jb. You can check that this is this. This is equal, now look at this. This is j to the a to involution to the power of involutions times the same involution. So this is a to the j to the power of b, a to the j, jb. Now we have this to the b, aj, so this is b to the jb, and so this is equal to j. So we have this property in characteristic 3, and so this is why sharply two transitive groups of characteristic 3 always split. And now I'm going to be bold and put a conjecture contrary to maybe what Ilya would say, and my conjecture is that for any characteristic other than 3, then 3, what? There exists a non-split sharply two transitive group, infinite of course, sharply two transitive group of that characteristic. Thank you.